Good morning. Welcome to Krishna's class. Last time we were discussing a lemma which is going to be a tool in our proof of an isometry theorem. But before that, I will come back to this lemma and then just review the various factors involved in it. But before all this, our objective is to prove a isometry theorem. In short, what we are going to say is that some subspace of the Hilbert of a given Hilbert space is isomorphic to L2, and this isomorphism or this isomorphism which is an isometry is determined through an orthonormal set of vectors. So let us look at an example. So we will just see an example and get a feel. A concrete example, and we will get an idea. Then we can go to the abstract version. Okay. So let us take a Hilbert space which is equal to L2 over the interval minus 1 to 1, a real Hilbert space. And this consists of all square integrable functions on the interval minus 1 to plus 1. Okay. That means all f such that integral minus 1 to 1 so this is the collection of vectors. They are functions defined on the interval minus 1. Now we consider the Legendre polynomials. Okay. So let me write down the. Let us consider Now you know that the Legendre polynomials are obtained through Gram-Schmidt process. So we consider the following functions: 1, x, the polynomials, x square, etc., contained in and you know that the inner product on this space is given by so we are considering only real functions, therefore there is no complex conjugation that is there. Okay, and this leads to this particular, which is the square of the norm of the vector f, induces, leads to norm f square. Okay. Okay, so this is what you have. So this defines a norm, etc. All those things are. This is an inner product. This is the induced norm. This defines the induced norm. Okay. Now, what we do is You are familiar with the so-called Gram-Schmidt process. Apply process to the polynomials x to the power n. Okay. This gives or defines the so-called Legendre polynomials. This defines the Legendre polynomials designated by now the PNP now the property that this collection has is the following. There is inner product of that means this forms an orthonormal set of polynomials minus 1. Okay, so that is the background of this, and these are the things which are worth looking into. What is a Gram-Schmidt process, but we are not going to do it. And this is a process of, from this set of linearly independent class of elements of L2 minus 1, 1, you apply Gram-Schmidt process to construct the PM, the Legendre polynomials, and they have this property. Okay, now let us consider a part of it. Okay, so consider let A be the set of numbers if you want you can put an here. Okay, so let us designate it by a. Then P naught Pn is the first n plus 1 Legendre polynomials obviously being which form a orthonormal. In L2 and L2 minus 1. So this is the collection that we are taking. So let M denote or Mn plus 1 define so let Pk or Mn plus 1 denote the span of these elements in the Hilbert space. What do we mean by this? So they are just finite linear combinations with coefficients picked from R, because R is the associated field that we are considering. Okay. Then what you have is this Mn plus 1 equal to the span of one t square t to the power n. And Mn plus 1 is a subspace of L2 and n plus 1 dimensional subspace of H. H is L2 minus 1 plus 1 of this Hilbert space. Okay, because you know that these are spanned by P0, P1, P2, Pn, which form an orthonormal set of vectors. And because of orthonormality, they are linearly dependent. Anyway, you can see that this Mn plus 1 is essentially the span of 1 t square, etc., e to the power n also. Okay, so that's about our Mn plus 1. Now, what we do is the following. Okay. Now choose a x belonging to H. That is an xt that's a typical element of H. Now let AI define the inner product of X with Pi for I belonging to so that's the notation. AI is this. And you consider, or we define, the n plus 1 dimensional vector Rn plus 1 belonging to Rn plus 1, and this is of course having the property that, okay, and one can easily prove that integral minus 1 to plus 1 equal to or the following. I'll write it this way. It is x t equal to this is what xt is all about. AIs are unique. And you also have the property that integral minus 1 to 1 this is equal to, if you use orthogonality, this is what you get. I equal to 0 to n n square. And this is of course finite. Okay, because this is finite, right? And now you see that the Rn plus 1 here can be identified with what is called L2. We have we used this A, okay, which consists of all A belonging to Rn plus 1, and in fact this is redundant. This is so it's an n-dimensional vector space. Okay. Now we shall define f from An by f of x equal to a, vector a, where ai, okay. So this is the identification then, which is equal to a. Okay, so f is defined from H to L2. Now, one of the properties that you immediately observe is that the okay. Now, this is for every x belonging to H. Okay. Now, one observes that Mn is a proper subset of H, that is, where x is u belonging to H, such that u is orthogonal to pi for every I belonging to okay. That is there because you have if you take Pn plus 2, that satisfies this criteria. Okay. So for example, Pn plus 1. In fact, there are a lot of vectors of this kind. Okay. Therefore, Mn plus 1 is a proper subset of H. Now, one of the implications of this is that the map F is not 1-to-1 on. Okay, that is easy to prove because you can see that if equal to, in fact, for any scalar multiple of u, if you add to x, then this is what you get. Okay, so this is not, the map is not 1-to-1. On the other hand, choose others. Then xt defined by is such that f of x equal to, therefore it is on to. So f is from is a map from h to mn plus 1. Okay. h to mn plus 1. Then this is on to. Then f of x is equal to a, which implies f is on. So the function f that we have defined may not be one-to-one, or in fact it is not one-to-one, but it is one-to-one. So that, let us save this result in our mind. Okay. Now another thing that you can so let x be ai y be pi. Then belong to n plus 1. Okay. Now then x minus y pi, and this of course belongs to m. Okay, you see that you apply this. Now compute this. So take this is equal to this is equal to this. Okay, because you know that f is linear. Of x minus y. Therefore, you see that a minus b this is in An and this is in N. This relationship is there, and F is therefore an isometry Now, one of the consequences of this is that F is an isometry of this is a result that you can get. And therefore, F is now an isomorphism of Fn plus 1 to what is that space? An L to An, which is the same as Rn cosine, which is isometry, which is an isometry. It's a very nice example because we work with what I call the Chandra polynomials, a very concrete example, and we have proved this result. Now let us try to foresee this result, how this result would appear in a more general setting. Now here one of the simplifications that we have resorted to is to take the index set as a finite set. Okay, so these are some of the drawbacks. So okay, so let us now generalize. And see this is what we are. Okay, so we will take the abstract version. Now, the limited version of this result possibly that we are going to write down is that note that this is a finite set. Okay. Further, we also note this result. We have for any x belonging to H, norm of sigma I equal to 0 to and this one, or we will put it this way. No. Less than or equal to this is what is called the Bessel's inequality that we have. Okay, this would be essentially. So this result would turn out to be helpful here. I can put it here. X belonging to H norm of x square and f of x This is the result that we have. This is essentially what is called the Bessel's inequality. Bessel's inequality is that. Now we shall now generalize the result and see whether it holds. So what do? We have H, an inner product, an orthonormal set, or what you call an index set. A may not be or even countable. It's some subset. It's an index set. Okay. So U alpha belonging to A has to be an orthonormal sequence in the orthonormal sequence, that is one and inner product of theta, and you see that so these results we have already. Okay. Now let span of linear combinations of belonging to A. Then M is subspace of H. Now you look at the corresponding situation here. There we had Mn plus 1. Okay, and Mn plus 1 is a subspace of H there. But Mn plus 1 is finite dimensional. Therefore, Mn plus 1 is a closed subspace. Here, M is a subspace of H. M is not necessarily a closed subspace. Therefore, you can now you know that in H the inner product induces a norm and the norm induces a metric. Okay, H is a metric space. It's a metric space. It is the induced metric. That means the metric induced by the inner product. Okay. So let M closure M closure may not be equal to, whereas in the case that we considered, so specific example we considered M closure equal to M. Okay. So M closure that means it's a proper subspace, but with a certain limitations. That is that. Now what we can do is, okay, for each H belonging to H, let X hat alpha an element of that is L2A. L2A is all Y such that y hat such that sigma y hat is finite. Then you have already seen that although this sum at the outset appears to be a uncountable sum, but essentially it is equal to, it's a countable sum, because you see that all but possibly a countable number of alpha, y hat alpha equal to 0. I mean, that's something that we have put earlier, okay, about the infinite sums, right? Therefore, I'll just make a caution here. Note that or even finite, but never a uncountable sum. It's possible, can be a finite sum also. Okay, y, that is y hat alpha is equal to 0 for every alpha belonging to A other than possibly countably many countably many alpha belonging to. See, last time we introduced all these things and we also gave the meaning of the sum sigma alpha belonging to A, sum y hat alpha. Okay. See, is called the Fourier coefficient now. Y belonging to L2 for y belonging to H. Okay. Therefore, what it means is that if you pick any element of H and compute the Fourier coefficients with respect to the orthonormal set U alpha. Okay. Then the all but countably many or possibly even finite, okay, of y hat alpha is 0, okay, right, for alpha belong. So this is the situation. Okay. Now you observe that M closure is a closed subspace of it's a closed subspace of H. M closure is a Hilbert space, is complete, and hence a Hilbert space in its own right. Okay. The theorem that we are going to prove is the following. So we prove the following. One, for every x belongs to H, sigma alpha belonging to, this is what is called the Bessel's inequality. Now this is true for every x belonging to H. Further, defined by is an isometry from M closure and V. This is the theorem that we are going to. Okay. So in short, I'll just put a schematic diagram that will be clear. So you have, this is X, this is M, and M closure is course, that means all points are also. So this is take M quotient. Now you have okay. So there is this phi defined from here. Sorry, f defined from here. That is, if you take an x here, then this is equal to alpha. Okay. Fx equal to x hat alpha for alpha belonging to P. Now this map is a continuous map. It's a continuous map from M closure on to L2A, or L2A is a replica of M, which is an so distance preserving map. What do you mean by isometry is this? That is distance preserving. That means here this is the result that you have for every xy belonging to. Okay, so that's the main theorem that we are going to do. See, you can see the generalization here from what we have considered in our example. Now it will be nice to re-examine the example and its generalization and have a complete understanding of the notations and so on. Now with this you know with this introductory discourse, now I state the theorem. So let us state the theorem. A is an index, of course. Orthonormal be the space of one finite linear combinations of now A need not be finite. Okay. Or even not even counting. That is then we make the following conclusions. Then summation over alpha belonging to A these are the Fourier coefficients. Now this is true, this inequality is valid for all x belonging to H. This is called the Bessel's inequality. X hat alpha are the Fourier coefficients of X. Of X. This is essentially inner product of X with U alpha. That is the meaning of that. If X hat designates A the map F H2 L2A given by hat into L2A is continuous on. Now the restriction of on M closure is a continuous one-to-one map to L2A, which is onto and is onto and onto and some. So the properties that you have are, first of all, this what is called the Bessel's inequality is satisfied. This is the statement of the theorem. So the conclusions are the Bessel's inequality holds good. That is the first one. Second one is continuous linear map which is a bijection means it is one-to-one and on-to and an isometry. So this is the result that we want to prove. Okay. So for that we prove a more general lemma which we have already explored last time and gear this whole problem into the language of this lemma so that you can immediately draw a conclusion. See, you have the right kind of about the isometry and onto the conclusions are here, the linearity etc. you will have to conclude from the circumstances because it's a very specific case that we have looked at. There it's a far more general result where we are not assuming these spaces are linear spaces. We are merely assuming they are just metric spaces. Okay, so let us read the theorem or the lemma. Lemma says, suppose that x and y are metric spaces, x is complete. We are not assuming x and y are linear spaces. We are just merely assuming they are metric spaces. And we also assume that this is a complete metric space. Okay. The second assumption is that f is a map from x to y, which is continuous. It's a continuous map. See, x has a dense symmetry. So that's an assumption that we make. And fx naught is dense in y. Now you see, it's a perfect tool to prove this theorem. Okay, because here is you take x enclosure. Okay, x to be enclosure. Enclosure is a complete is a closed subspace of a Hilbert space. Therefore, by itself, it's a Hilbert space, and therefore it's a complete metric space. So instead of x, we choose enclosure. X naught we take as M. Okay. Then we have the f is defined properly. Then f is linear from M to L to A. Okay. Because we take y to be equal to, that's the assumption, and f is defined from M to L to A, and f is then such that f is linear. Okay, the way in which we define it follows that it's linear. And also you can show that it's an isometry. Of course, M is dense in closure. Is an isometry from M to L to A. Okay. Then we have, of course, M is dense in, or we have to prove that f of M is in fact it is the whole of that. Okay, right? And that the conclusion that we can draw is that f is an isometry from M closure to L to A. Okay, so that's how we attempt a proof of this, right? That's how we use this theorem, and this is a far more general result than the one that we are proving in a different context. Okay, because we are going to apply this lemma in its as a convenient tool in the proof of our theorem. So let us prove this theorem. Not the lemma. This lemma we have already. We have already outlined the proof by setting this framework. Okay, so that you can apply this lemma. Okay. Okay, what we do is, so this is the statement of the theorem. Let us now have the following. Define H2 by x hat. Okay, where x hat alpha this belongs to L2. This is not difficult because we are just defining this one. And what do you have? You take x and you see the collection that we take is, so you take okay. So F is a mapping from H into L to A. So all that you have to prove is this. So that it's an element of L. Okay. Now this is a consequence of what you call the Bessel's inequality. That is, we have alpha belonging to A whole square. Now this is true for all finite so let me just write. This is true for all finite A tilde contain. Hence, it is true for all of, that is sigma is finite. Okay, therefore L2. That's the proof of that. Okay, now it's easily seen that F is all that we have to prove is this: F of fine F of Cx. So you can prove this easily because by just using the function of F. Okay. Now apply the Bessel's inequality. One, two, x minus y then we have this is the L2 norm. This is equal to 2 norm, and this is of course less than or equal to norm of x minus. Okay, this is the Bessel's inequality. This implies so f is a continuous linear. Okay. Now clearly f restricted to m is an isometry of dense subspace of and today because this might consider this would have only finite subs. Okay, this particular subspace will consider only finite subs because you see that we are picking up elements from in M they are finite linear combinations of x alpha. Okay. Is finite yes. That means essentially the sum is going to be on some f this is going to be on some subset depending on what x you take. So x alpha okay, then put it this way is a finite to support is finite a subset okay. Now M closure is a complete Hilbert spaces. And hence a complete metric space. Now apply lemma above with H enclosure x naught equal to m H is equal to enclosure x naught m and then f of alpha beta a y equal to then we conclude that f is a one-to-one onto map from enclosure to enclosure to the f is linear, f is linear and f is onto already f is an isometry onto merely the application of this here. So that's why we geared everything in language. And this is also one of the techniques that we often use. Sometimes, you see, this theorem, you can directly write down the of all this with all the details. But sometimes, when you see that there is some substance in the method and a possibility of generalization, then we put everything as a lemma. And then, in a far more general context, because the general context is that here we are not assuming x and y are linear spaces. We just assume a set of conditions on f. Okay, and then from that you conclude f is an isometry of x onto y. So here we conclude that f is an isometry of enclosure onto L. This is what we wanted to conclude. And this f that we have defined is naturally a linear factor. Okay, thank you very much. Yeah, before I wind up, I will also say that now what we have shown is you have started with a Hilbert space. You have taken a subspace of that. What we have shown is that the closure of that subspace is isomorphic to L to A, where A is, see, we are not assuming that the index set A and the collection U alpha takes care of all the possible orthonormal elements in the space. It's only a collection of orthonormal, a set of orthonormal elements. Now there may be many more orthonormal elements which can be adjoined. Okay. So every time you have a M, it has an enclosure, and that enclosure is isomorphic. So this is the isomorphism theorem, as well as the isomorphism has the speciality that the isomorphism that we have defined as a speciality is that it is also an isometry, or between two elements of the space, the distance is preserved under this manner. Thank you. Nice result.